Today we are going to look at projectiles that are being launched on an angle. So let's get started. So imagine that you have a projectile, something that's being launched, and it's fired at a velocity of 5 meters per second. So there's a couple things that you have to pay attention to. You have to pay attention to the angle at which the projectile was fired at. So if the angle was launched horizontally, meaning just straight across your theta, your angle was 0. If we know that the initial velocity was 5 meters per second, then the velocity in the horizontal direction is going to be 5 meters per second, and the initial velocity vertically is going to be 0. Now, in a different situation, still we have our projectile that is being launched with initial velocity of 5 meters per second, but if it's being launched straight up and our theta is 90 degrees, well, now we know that our initial vertical velocity is going to be 5 meters per second, and the initial horizontal velocity is going to be 0 meters per second. If the angle is not 0 or 90, the initial velocity is going to be part vertical and part horizontal, meaning it's being launched on an angle, and we have to think about what's going on horizontally and what's going on vertically. So imagine for a moment that you're watching an object as it rises into the air after it is kicked upward at an angle. So a soccer ball, a football, it's being kicked up into the air, and you're watching, you're observing at all these different points. My first question is, what happens to the horizontal velocity as it makes its way up and all the way back down? So if you look, I have different colored arrows on this diagram. So horizontal are these blue vectors. So if you look, as it makes its way up and comes back down, does anything change about these blue vectors? And you should be saying no to yourself right now. They're all the exact same length, meaning that the velocity is the exact same amount, has the exact same magnitude, and the arrows are all pointing to the right, meaning they have the exact same direction. So the horizontal velocity does not change as the object is rising up and falling back down. Then I want to ask, how does the velocity at A and G compare? So since it is not, the angle is not 0 degrees, it's not 90, so we have to separate horizontal velocity and vertical velocity. So we have already talked about that at points A and G, the horizontal velocity is the exact same. If you look at your red arrows, that's showing what's going on with the vertical velocity. So if you look, this vertical velocity, the length of that vertical velocity compared to the length of that vertical velocity, it appears that the length of those vectors are the exact same, but the direction of those arrows are opposite. So we could say that the magnitude of the velocity is the same, but it's opposite direction. So that initial velocity up right here is we could say positive 20, and at this point it could be negative 20. I'm just making up a number. And then we know as you toss an object straight up, we know that the velocity is going to decrease, as long as nothing else is affecting it, by 9.81 meters per second every single second. So you can see as it rises, these red arrows are getting smaller and smaller until it reaches its maximum point, D, where there is no red vector, which means that that vertical velocity at the maximum height is going to be 0. And then it's going to start falling back down at a rate of 9.81 meters per second squared. So now we're going down, and these red arrows are getting longer as it makes its way down. So you can see at C and E, those appear to be at the exact same height, same velocity, just opposite direction, or I should say same speed, opposite direction. Same thing with B and F, same speed, opposite direction, and we've already talked about A and G. So thinking about what we just talked on the last slide, we can use some of this information for its vertical movement to help us figure some things out and make some calculations. So again, it doesn't matter if you drop something, you toss it straight up, you throw it at an angle, you throw it horizontally. We know that all of those examples are free fall examples, and our acceleration value is always going to be 9.81 meters per second squared. So that's something that we need to take in mind. So, and then we also know that we can use that information to help us calculate the initial vertical velocity of the object, because if it's being tossed at an angle, it's not, the initial velocity is not going to be 0. So we're going to have to calculate that if it's not given to us in the problem. And then we also know at its maximum height, we saw on that last slide that there wasn't a red vector up midway point, meaning the maximum height. We could say that that velocity at that point is 0. So if we know from here, if we are able to calculate that initial vertical velocity, we could say that the final velocity at the halfway point at that maximum height is 0. And then we also know what we talked about on the previous slide, at points A and G, they had the exact same speed, just opposite direction. So if we know that initial vertical velocity up, then we know the final vertical velocity right before it hits the ground. So let's solve some problems. So we're still going to use all of our acceleration formulas, but we're going to, since it's on an angle, we have to separate what we know horizontally and what we know vertically, so we're just going to solve it a little different than our other projectile and our acceleration formulas. So this problem says you kick a soccer ball at an angle of 40 degrees above the ground with a velocity of 20 meters per second. We are going to calculate how high it'll go, how much time it spends in the air, how far away from you when it hits the ground, so we call that the range, and what is the ball's velocity when it hits the ground. So whenever I am solving a problem when it's something that is being launched on an angle, I like to separate what I know horizontally and what I know vertically. So I set up a horizontal and a vertical column. So I make an X and a Y column and list what I know vertically and what I know horizontally. On that previous slide, when I showed you the object that was launched up, and I asked you what do we know at point A and what we know at point G, and what do we notice about the horizontal velocity as it made its way up and as it came back down, we saw that those blue vectors were the exact same length as it went up and came back down. So that means horizontally, it's moving at a constant velocity horizontally. So there's only going to be one equation that we're going to use for the horizontal column, which is going to be x equals vt. That is the only equation that you're going to use for horizontal, so you're only ever going to have 3 variables in this column. Over here in my vertical column, we know it's going to go up and come back down. So the velocity, the arrows got smaller as it made its way up and then started to get larger as it made its way down. So the velocity is changing vertically. So we have to think all those acceleration formulas over here. So over in this column, we could use our VF equals V naught plus AT, changing velocity. If we don't know the time, you can use your VF squared equals V naught squared plus 2A delta X. We could also use delta X equals 1/2 AT squared plus V naught T, or delta X equals 1/2 T times V naught plus V final. So all of those that have changing velocity, you're going to only use for the vertical column. And again, this is the only equation we're going to use for the horizontal problem, because again, as the object rises and falls, the horizontal velocity does not change the whole time. It's constant velocity, and this is our only equation for constant velocity. So the first problem asked how high it'll go, and it got copied a little funny, but you can still read it. So if you're thinking how high it'll go, you need to think vertical, because the height is vertical, not horizontal. So it was told that the soccer ball was kicked at an angle of 40 degrees above the horizontal with a velocity of 20 meters per second. So it's not telling me the vertical or the horizontal, it's telling me my hypotenuse. So this vector here was 20 meters per second. So this vector is part horizontal, part vertical, And if I want to know how high it'll go, I want to just know the vertical velocity. I don't care anything about the horizontal part. I just need to know something about the vertical velocity. So I can use my trig functions to solve for the vertical velocity by using sine opposite over hypotenuse. So once I do that, I know the vertical velocity is 13 meters per second. So I can write that in here, 13 meters per second. And we know as it goes up, my acceleration is always going to be 9.81. So again, when I make that column, my x and my y column, all this information over here would be written down over here. So I know that the acceleration is the whole time is going to be negative 9.81 because it's going to go up, slow down, and then speed up as it comes back down. So the whole time the acceleration negative 9.81. And then right here, as it's kicked, that velocity right there is 13. And over here, right before it hits the ground, that velocity is going to be negative 13. And we also know at the highest point, that velocity is going to be 0. So we can say that the velocity at the maximum height, or we can say at the peak, is 0, which is this point. And then the initial velocity right here, as it goes up, is positive 13, and the acceleration the whole time is negative 9.81. And again, it's slowing down as it makes its way up, so we have to have opposite signs for my acceleration and my initial velocity. So we're solving for delta x. The only other variable I don't know is time, so there's only one equation I can use if I don't have time, which is vf squared equals v naught squared plus 2a delta x. So when I plug the variables in over here into this equation, I get a displacement of 8.61 meters. So as it's kicked, it's going to go a height of 8.61 meters above the ground. So the next question asks, how much time does it spend in the air? And again, you need to think vertical, because in your xt, xy column, again, we have x, v, t here. We have no information over here that we know. We could solve for this velocity by using cosine of the triangle that we did on the last slide, but we still, in order for us to solve for time, we would have to know how far horizontally it goes, and we don't know that. We do have a lot of information over here in the y column. All this information we know is over here in our y column. So it's better for us to think vertical when it's asked how much time does it spend in the air. So I know, again, at the maximum height, that velocity at the maximum height is 0. The initial velocity as it's kicked up is 13. The acceleration the whole time is negative 9.81. And we just solved for on the last slide that it goes up 8.6 meters above the ground. So at the maximum height, it's 8.6 meters above the ground. So we want to solve for time. So really, again, there's always more than one way that you could solve the problem. Over here, we could solve for how long it takes to make its way up to that halfway point, and then double it, and we know that it takes that exact same amount of time to go back down. So if we solve for the amount of time it takes just to go halfway up, we can say that the final velocity at the maximum height is 0. The initial velocity as it makes its way up vertically is 13. The whole time my acceleration is negative 9.81. So to go from this point to this point, it takes 1.325 seconds. So 1.325 seconds here, and another 1.325 seconds here. So doubling that, the whole time it takes me 2.65 seconds. Another way you could think about it is here. We know, like I showed on your last slide, this velocity here is the same as that velocity there. So this was positive 13, this was negative 13 right before it hits the ground. So we could think about it going from this point to this point. So we know the velocity right before it hits the ground is negative 13. The velocity right here is a positive 13. The whole time your acceleration is negative 9.81 because it slows down and then speeds up. And again, you're going to get the exact same answer. So either how, it doesn't matter how you think about it, you're going to get the exact same answer.